Right now, you are being hit by a particle storm so intense the numbers almost stop meaning anything, and you still feel absolutely nothing. But before we continue, please subscribe to the channel to give your support. Let's continue. Every second, about 60 to 100 billion solar neutrinos pass through every square centimeter of your body. That's per square centimeter. If you like imperial units, that's roughly 100 trillion neutrinos through every square inch of you, every second. Hold out your hand, look at the back of it. That area is being hammered by more neutrinos in one blink than the total number of sand grains on all of Earth's beaches. They're flying in from the core of the sun, about 150 million kilometers away, around 93 million miles. Traveling just under the speed of light. They don't stop at your skin. They don't care about your bones. They don't even see the planet. Almost all of them go straight through you, then straight through Earth, and keep going into deep space as if none of this mass is here at all. So the obvious question is, if this is happening all the time, why don't you notice anything? Ever? To answer that, you need to know how picky neutrinos are. Neutrinos only respond to two forces in any serious way: gravity and the weak nuclear force. Gravity is incredibly weak at the particle level, so you can ignore that for interactions inside your body. The weak force is the only one that really matters for neutrinos hitting matter. They have no electric charge, so they don't feel electromagnetism the way electrons and protons do. Light, which is made of photons, interacts with the electric charges in your atoms all the time. That's why you can see things. That's why light gets absorbed and scattered and reflected. Neutrinos skip that whole system. No charge means no pull, no push, no friction with the electrons around you. Physicists describe how likely a neutrino is to hit something with a number called the interaction cross-section. You can think of it as the effective target size of a proton or neutron as seen by a neutrino. For typical solar neutrinos with energies of a few million electron volts, that effective area is insanely small, way smaller than the size of an individual proton, way smaller than the size of an atom. For higher energy neutrinos in the billion electron volt range, that effective area grows, but it's still tiny. Your body is full of atoms, but from the neutrino's point of view, those atoms barely present any target at all. Most neutrinos just slide through empty space between nuclei and electrons and never come close enough in the right way to trigger a weak interaction. So from the neutrino's perspective, you are not a solid object. You're more like a very diffuse cloud, mostly empty volume with a few scattered points that almost never line up with its path. That raises a second question. If you're basically transparent to neutrinos, how far could one actually travel before it finally hits something? Here, the scale becomes ridiculous. A standard rule of thumb in particle physics is this: a typical solar neutrino could travel through about a light year of solid lead before it has a good chance of interacting once. 1 light year is about 9.5 trillion kilometers, roughly 6 trillion miles. Lead is much denser than your body, or rock, or iron. Fill that entire distance with lead, and a typical neutrino still probably gets through without a single interaction. That estimate comes from combining two things: how many nuclei you can pack into a volume of lead, and how small the interaction cross-section is for neutrinos at those energies. You multiply the number of possible targets by the probability of each hit, and only when you stack up a completely absurd amount of material do the odds start to become likely. Now, compare that to human and planetary scales. Earth's diameter is around 12,700 kilometers, about 8,000 miles. That's nothing next to a light year. So for the solar neutrinos passing through you right now, the chance that any one of them hits something while passing through the entire Earth is very low. Most of them enter on one side of the planet, traverse mantle, core, mantle again, and exit the other side like the planet is a slightly thicker patch of vacuum. This leads to another problem. If neutrinos almost never interact, and if a light year of lead barely slows them down, how do we know they exist? And how do we study them in the first place? The key is the enormous number of neutrinos. Even if each individual neutrino has a tiny chance of interacting, the total number that hit Earth is so huge that rare events still happen. The flux at Earth, those tens of billions per square centimeter per second, multiplied over the entire surface of the planet and over long times, gives you a gigantic number of attempts. If you provide enough material as a target and you wait long enough, you do get collisions. So detectors are built on a very simple strategy. Use a ridiculous amount of matter as a target. Make it as clean and quiet as possible, and look for very rare, very faint signals. That's why some detectors use tens of thousands of tons of ultra-pure water, or liquid scintillator, stored in underground tanks the size of office buildings. Others, like the IceCube experiment, use about a cubic kilometer of Antarctic ice, instrumented with thousands of sensitive light sensors. Every so often, a neutrino hits a proton or a neutron in that material, producing charged particles that move fast enough through water or ice to emit a faint cone of blue light. Arrays of photometric tubes, basically extremely sensitive light detectors, pick up these flashes. Most of the time, you only get background events from cosmic rays and natural radioactivity, so these experiments go deep underground or under ice to shield themselves. After you cut away that background as much as possible, what's left are real neutrino interactions. The rate is still small. You might get a few dozen solar neutrino events per day in a huge detector, out of the mind-blowing number that pass through. But those few events are enough to map the flux from the sun, measure their energies, and confirm that this invisible storm is constant and real. And this brings us to the most unsettling conclusion of this section. Before we even properly define what a neutrino is, you've already learned that your normal sense of solid is not fundamental. Your body, your walls, the planet itself are only solid to the forces you're familiar with, mainly electromagnetism. To neutrinos, all of that is almost transparent. In the language of neutrinos, Earth is just a slightly denser region of mostly empty space, where the chance of a hit goes from basically zero to still tiny, but not completely zero. This means that our everyday picture of matter, as solid and impenetrable, is just a local, low-energy view. On the particle level, most of the volume in atoms is empty, and some particles can fly through almost all of it without noticing. Neutrinos are the most extreme example of that, and they expose how flimsy matter really is when you stop thinking like a human-sized object and start thinking like a weakly interacting particle. So now the tension is this. We know there's a particle streaming through you every second by the trillion. We know it barely interacts. We know it can cross a light year of lead. And we know we can still catch it with gigantic, quiet detectors buried under rock and ice. But we still haven't answered the core question. What exactly is this thing? What kind of particle is so stripped down and so minimal, but it can cross a planet as if it was not there, and still turn out to be essential for how stars, supernovae, and the early universe work at all? You've just heard that neutrinos sail straight through you and through Earth, so now you need to know, what actually is this thing that ignores almost everything and still matters so much to the universe? On paper, a neutrino looks almost boring. It belongs to the lepton family, same family as the electron, but stripped down. It has no electric charge, so it doesn't feel electromagnetism, and it has an incredibly small mass. Right now, the best direct measurements from the Katrin setup in Germany say that the mass of the electron-type neutrino is below about 0.45 electron volts. In plain terms, that's less than a millionth of the electron's mass, and in kilograms, that's around 8 times 10 to the power of minus 37 kilograms, a number so small it's basically zero for everyday life. There are 3 known types, or flavors, of neutrino: electron neutrino, muon neutrino, and tau neutrino. Each one is tied to a charged partner, the electron, the muon, and the tau. They all share the same basic behavior. No electric charge, almost no mass, and they only really feel two forces: gravity, which is irrelevant at this scale, and the weak nuclear force. They have no color charge, so they don't feel the strong nuclear force that holds protons and neutrons together, and with no electric charge, they don't interact with light. That's the whole list of things they respond to. Here's the twist. That tiny mass, which sounds like a detail, already breaks the original version of the standard model of particle physics, which treated neutrinos as exactly massless. The fact that the mass is small, but not zero, tells you straight away that the standard model is missing something important in how particles get their mass. So you end up with this paradox. The simplest, most stripped-down particle you can write into the theory ends up being the one that proves the theory is incomplete. So where do these things actually show up in the real world? Where do neutrinos get made in a way that matters to you? Neutrinos appear whenever the weak force is at work, changing one type of particle into another. Take beta decay, a classic nuclear process. Inside a radioactive nucleus, a neutron can turn into a proton. When that happens, the nucleus spits out an electron and an electron antineutrino. That antineutrino is a neutrino of the electron flavor, with opposite lepton number. It flies out at high speed, and in most cases, nobody ever sees it. In the core of the Enrico Fermi sun, protons fuse together to make helium. Along the way, some of those protons have to turn into neutrons. That change also uses the weak force, and when it happens, neutrinos are built into that reaction network from the start. On Earth, particle accelerators smash protons into fixed targets at high energy. Those collisions produce short-lived particles, like pions and kaons. Those then decay into muons and muon neutrinos, and later the muons decay into electrons, more neutrinos, and more antineutrinos. The whole chain is driven by the weak interaction, and neutrinos are how the process balances the bookkeeping for energy, momentum, and lepton number. The key idea is this. If the weak force is changing one type of particle into another, somewhere in the equation there is almost always a neutrino or antineutrino taking away some energy and carrying away the right kind of lepton number to keep the rules consistent. But there's a deeper story here. Neutrinos weren't discovered because someone saw them in a detector first. They were invented on paper to fix a problem that made physicists think nature might be breaking its own rules. Early measurements of beta decay showed something weird. If a nucleus emits an electron, and you know the mass difference between the starting nucleus and the ending one, you expect the electron to come out with a fixed energy, a sharp line in a graph. Instead, experimenters saw a smooth spread of energies, from low values up to some maximum. It looked like energy conservation had failed. This was not a small annoyance. It threatened one of the core principles of physics, that energy is always conserved in isolated systems. In 1930, Wolfgang Pauli proposed a desperate solution. Maybe there is an additional neutral, very light particle emitted in beta decay, a particle that carries away the missing energy and momentum, but that nobody had seen yet because it interacts so weakly. He even apologized for introducing a particle that might never be detected. Later, Enrico Fermi built this idea into a full theory of beta decay, with a new field and new interaction terms. Decades after that, experiments at nuclear reactors finally saw neutrinos directly by watching for rare interactions in large tanks of fluid near reactor cores. When physicists included this invisible neutrino in their calculations, the electron energy spectrum from beta decay suddenly made sense. The spread of energies wasn't a failure of energy conservation. It was just the visible part of a two-body share. The electron gets some, the neutrino gets the rest, and together they add up exactly to what you expect. So neutrinos start their life in physics as a bookkeeping fix, an unseen term you have to add so the numbers stop lying to you. But they do more than fix the numbers. They also expose a built-in bias in how the universe handles left and right. Neutrinos, like electrons, have a property called spin 1/2. You can think of it as a kind of built-in angular momentum, a quantum version of which way the particle tends to point. For moving particles, you can compare the direction of the spin with the direction of motion. If the spin points opposite to the motion, we call it left-handed. If it points in the same direction as the motion, we call it right-handed. Here's the strange part. In all weak interactions we have ever observed, neutrinos only show up in one-handedness, left-handed, and antineutrinos only show up right-handed. The weak force simply ignores right-handed neutrinos and left-handed antineutrinos as far as we can tell. When physicists look at the directions that electrons and neutrinos fly out in nuclear decays, they see a clear preference. The angular distribution is not symmetric if you flip left and right. This is called parity violation, and neutrinos sit right in the middle of that story. So neutrinos are not just neutral, almost massless particles. They are also locked into a specific handedness in the way they interact, which makes them a prime example of how the weak force cares about left versus right. Now, put all of this on one table and look at the pattern. You have a particle with no electric charge, so it doesn't talk to light. It has no strong force charge, so it doesn't get glued to nuclei. It has a tiny mass, so gravity barely affects its path on human scales. It only interacts through the weak force, which already has very low interaction probabilities at low energies, and even then, it only couples in one-handedness. That set of properties is exactly the recipe for a particle that passes through almost everything. When a neutrino crosses your body, the only way you know it was there is if, by extreme chance, it triggers a weak interaction with the right-handedness in one of the nuclei inside you. Almost all of them fail to do that, so they just keep going. But now, flip the picture. If you tried to remove neutrinos from the universe, everything that uses the weak force would break. Beta decay would not work properly. The fusion reactions in stars would not look the same. Supernovas would not be able to dump energy out of their cores fast enough, and the energy balance in a huge range of nuclear and particle processes would be wrong. Neutrinos are the channels that let energy leak out of dense nuclear environments without constantly slamming into matter. So, a neutrino is not just a little neutral particle. It is the bare minimum package of properties the universe seems to need when it wants to move energy and information from one place to another through matter while touching almost nothing on the way. That raises the next question. If neutrinos are this minimal, this hard to stop, and this essential, where are they actually being produced in the universe? How do you end up with the insane numbers that are blasting through your body right now? And what do those production sites tell you about stars, supernovas, and even the Big Bang itself? How do you end up in a universe where neutrinos are so common that trillions are passing through you second without a break? Start with the sun. Every second, it fuses around 600 million tons of hydrogen into helium in its core. A small part of that mass becomes energy, and a built-in part of that energy flow is carried away by neutrinos. When you do the physics, you get a predicted neutrino flux at Earth of roughly 6 to 8 times 10 to the power of 10 neutrinos per square centimeter per second. In imperial units, that's on the order of tens of trillions per square inch per second. Neutrinos escape the solar core almost instantly, in a couple of seconds, and then travel the 150 million kilometers, about 93 million miles, to Earth in 8 minutes. Photons made in the same fusion reactions take hundreds of thousands of years to random walk out of the solar interior. So when you detect solar neutrinos, you're reading the sun's core power output live, 8 minutes old, while the sunlight on your skin carries information that was locked up inside the star long ago. Once you account for the fact that neutrinos change flavor on the way here, the measured flux in big detectors lines up well with those solar models. If a stable star like the sun already floods you with neutrinos, what happens when a massive star stops being stable and starts dying? When a really massive star runs out of fuel in its core, gravity wins. The core collapses inward in a fraction of a second. The densities and temperatures blow up, and the physics switches regime. In that collapse, almost all of the gravitational energy released, roughly 10 to the power of 46 joules, doesn't come out as light. It comes out as neutrinos. That's more total energy than the sun will radiate across all wavelengths over its entire 10 billion year life, and it leaves as a burst lasting only a few seconds. In 1987, a blue supergiant in the Large Magellanic Cloud blew up as supernova 1987A, about 168,000 light-years away. Several underground detectors on Earth, built for other purposes, recorded something unusual: a few dozen neutrino events arriving over about 13 seconds. No bright flash, no explosion yet, just this neutrino pulse. Hours later, telescopes saw the star appear as a supernova. The times, directions, and energies of those few dozen neutrinos lined up perfectly with core collapse models. That tiny dataset was enough to prove that neutrinos can escape a collapsing core while it's completely opaque to light, and that they are the main energy channel in one of the most violent events in the universe. That's nature's side of the story. But can you make your own neutrino sources on demand here on Earth? Nuclear reactors are exactly that: controlled fission machines that double as intense anti-neutrino sources. A typical commercial reactor putting out about 3 gigawatts of electric power, which means around 10 gigawatts of thermal power, produces on the order of 10 to the power of 20 anti-neutrinos every second. That's 100 billion anti-neutrinos streaming out in all directions. Experiments place detectors tens to hundreds of meters away, sometimes a kilometer or so, and watch how many antineutrinos are caught as the reactor power goes up or down. By comparing near and far detectors, you see that some electron antineutrinos disappear as they travel, not because they stop, but because they change flavor into types your detector is less sensitive to. That's how several reactor experiments pin down one of the mixing angles in neutrino oscillations. The same principle also lets you monitor whether a reactor is on and roughly what its fuel state is by just watching the neutrino rate through thick concrete and rock. On the accelerator side, labs like Fermilab and JPark slam high-energy protons into targets, make beams of pions and kaons, and let those decay into muon neutrinos. Magnetic fields steer the unwanted charged particles away, and what's left is a neutrino beam that goes straight through Earth. Detectors hundreds of kilometers away measure how many muon neutrinos arrive, and how many have turned into electron or tau neutrinos. The way those numbers change with distance and energy is direct, controlled, human-made evidence that neutrinos don't keep a fixed identity in flight. So stars and reactors give you today's neutrinos, but the universe has been making neutrinos since the very beginning. What about the first factory, the Big Bang itself? Go back to when the universe was less than a second old. Temperatures were around 10 billion Kelvin. Everything was a hot plasma of photons, electrons, positrons, neutrinos, antineutrinos, and a few nucleons, all colliding constantly. In that state, neutrinos were in thermal equilibrium with everything else, constantly being created and destroyed. As the universe expanded and cooled past an energy scale of around 1 mega-electron volt, interactions slowed down. Neutrinos stopped scattering often enough to keep up, and effectively decoupled. From that point on, they have been flying freely through space. Today, that ancient neutrino bath should be cooled to a temperature of about 1.95 Kelvin, just a bit colder than the cosmic microwave background. There should be roughly a few hundred of these relic neutrinos in every cubic centimeter of space, including the air around you. We have not yet detected them directly because their energies are incredibly low and their interactions are even rarer than normal, but their presence shows up indirectly in how fast the early universe expanded, in the pattern of ripples in the microwave background, and in the predicted abundances of light elements like helium and deuterium from Big Bang nucleosynthesis. Those cosmological checks all point to a sea of relic neutrinos still filling every cubic meter, a fossil signal from the first second. That covers the cosmic scale, but there is also a constant low-key neutrino source right under your feet. Inside Earth's mantle and crust, heavy elements like uranium-238, thorium-232 and potassium-40 are slowly decaying. Many of those decays are beta decays, which means they emit electron antineutrinos. These are called geoneutrinos. A few large detectors, originally built for reactor and solar neutrino physics, are sensitive enough to pick out a small excess of antineutrino events coming from below, with energies in the right range for these radioactive chains. By measuring how many geoneutrinos they see and combining that with geological models, scientists can estimate how much of Earth's internal heat comes from radioactive decay versus leftover heat from formation and core processes. The total heat flow out of Earth is around 40 to 50 terawatts. Geoneutrino data suggests that a significant fraction, maybe about half, is radiogenic. That links neutrino measurements directly to things like plate tectonics, volcanism, and the planet's long-term cooling. You are literally using almost non-interacting particles to do calorimetry on an entire planet. So now you have the full picture of production. The sun and other stars are steady fusion factories. Core collapse supernova dump almost all their energy out in neutrinos in a few seconds. Reactors and accelerators on Earth create controllable beams. The Big Bang left a background of relic neutrinos everywhere, and radioactive elements inside Earth add a constant whisper from below. The universe is not short on ways to make neutrinos. It is saturated with them. That sets up the next problem very sharply. If neutrinos are being produced in such insane numbers in stars, supernova, reactors, and the early universe, why do they still almost never hit anything? Why can something be that common and still almost never hit anything? The honest answer is, it's just a numbers game, and the numbers are brutal. When a neutrino passes through matter, the chance of it interacting is set by something called the weak interaction cross-section. You can think of it as the effective target area a proton or neutron presents to the neutrino. For the kind of neutrinos coming from the sun, with energies of a few million electron volts, that cross-section is around 10 to the minus 44 square centimeters. For higher energy neutrinos, like the ones from accelerators or cosmic rays, up in the billion electron volt range, it grows to about 10 to the minus 38 square centimeters. Those exponents matter. 10 to the minus 44 is a decimal point followed by 43 zeros before you even see a 1. Now compare that with how many particles you can pack into matter. A cubic centimeter of solid material, about the size of a sugar cube, has roughly 10 to the 23 atoms in it, and each atom has protons and neutrons. That sounds huge, but it is nowhere near the 10 to the 38 or 10 to the 44 you would like if you wanted a decent chance for a single neutrino to hit something as it passes through. Even if you stack up kilometers of rock or the whole diameter of Earth, you're still way below the target count that would make interactions common. So from the neutrino's point of view, most of the time it's flying through vast amounts of almost completely empty space. The matter we care about just doesn't add up to enough nucleons in the right spot at the right time to make interactions anything more than a rare exception. This becomes easier to see when you compare neutrinos with particles you're more familiar with. Photons interact through electromagnetism, which is strong at the atomic scale. A visible photon trying to cross a centimeter of water, about half an inch, will almost certainly be absorbed or scattered in that distance. Its mean travel distance before something happens, its mean free path, is on the order of that centimeter. That's why water looks opaque over long paths, and why your hand blocks light. A proton moving through air feels both the electromagnetic force and the strong nuclear force in collisions with nuclei. Depending on its energy, it can be stopped or significantly slowed within meters, or even less. That's why we can shield ourselves from many charged particles using just a few centimeters of metal or a concrete wall. Neutrinos are a different story. Their mean free path in matter can be many light years of solid rock, not centimeters or meters. A light year is about 9.5 trillion kilometers, around 6 trillion miles. That's how far light travels in a year in vacuum, and you would need that much dense material in one line before a solar energy neutrino has a good chance of hitting something once. That is why we can safely put neutrino detectors under mountains or under 2.5 kilometers of Antarctic ice, about 1.5 miles. The overlying rock or ice stops almost everything that interacts strongly or electromagnetically, but neutrinos come straight through to the detector almost unchanged. So they're hard to hit at low energy. But does that stay true if you crank the energy up? There is a twist. The higher the neutrino energy, the bigger the interaction cross-section gets. It is still small, but not as absurdly small. For ultra-high energy neutrinos in the tera-electron volt to peta-electron volt range, like the ones seen by the IceCube detector, the cross-sections are large enough that Earth actually starts to become noticeably opaque. Downgoing neutrinos, which skim the atmosphere and hit the detector from above, are more common at those energies, while upgoing ones, which have had to pass through the entire Earth first, are rarer, because a non-negligible fraction have finally interacted and been absorbed on the way. By measuring how the event rate changes with neutrino energy and with arrival direction, experiments can back out how often neutrinos must be interacting inside Earth. Then they compare those results with the predictions from weak interaction theory. So the same effect that makes neutrinos ghost-like at low energy becomes a direct measurement tool at very high energy, telling us that the cross-section grows with energy exactly the way the theory says it should. That brings up a deeper question. Why is the weak force so weak in the first place? What is it about this interaction that makes the cross-section so tiny at everyday energies? At the fundamental level, the weak force is carried by heavy particles called the W and Z bosons. Their masses are around 80 to 90 billion electron volts. That is huge compared to the energies of solar neutrinos, reactor neutrinos, or most radioactive decays, which are in the million or billion electron volt range. When a low-energy neutrino interacts with a nucleon, you can think of it as trying to exchange one of these very heavy W or Z bosons for a very short time. The heavier the messenger, the shorter the reach, and the lower the probability that the exchange happens. In more technical language, at energies much lower than the W boson mass scale, the effective interaction scales roughly like the neutrino energy divided by that huge W energy scale squared. If you plug in a few million electron volts for the neutrino and tens of billions of electron volts for the W boson, you get a suppression factor that is tiny. That's why we call it the weak interaction. It is not weak because of some vague label. It is weak because the particles that carry it are so heavy that low-energy processes barely manage to use them. So when you see neutrinos cruising through the planet, that behavior is just a direct consequence of heavy, weak bosons and low-energy neutrinos combined with the small size of nuclei. There is no extra trick. The important thing to keep in mind is that none of this is magic. Neutrinos don't pass through everything because they are immaterial or because they step out of normal physics. They pass through because the numbers baked into the weak interaction give you extremely tiny cross-sections at the energies we usually see, and because the amount of matter along their path just isn't enough to compensate. In principle, you could build a shield thick enough to stop almost any given neutrino. For a typical solar neutrino, though, you would need more lead in that shield than exists in the entire solar system, and that's obviously not happening. Their ghostliness comes straight out of equations that match what we see in reactors, in particle accelerators, in deep underground labs, and in detectors buried under polar ice. The same rules that let neutrinos sail through your body unchanged are the rules that let us calculate supernova cooling, predict detector rates, and design future experiments. And that sets up the next tension. If neutrinos are this hard to interact with, yet we're still catching them, how do you actually build a machine that can see them? What kinds of detectors do you need to spot the tiny moments when a neutrino finally does hit something? And how do you tell those tiny signals apart from the constant noise of everything else the universe is throwing at you? How do you build a machine to see something that almost never touches anything, a particle that mostly ignores an entire planet? The answer is, you go big, you go deep, and you accept that almost everything you record will be boring background. To catch more than a handful of neutrinos per year, you need a ridiculous amount of target material and serious shielding from all the other junk the universe is throwing at you. That's why a detector like Super-Kamiokande in Japan uses about 50,000 tons of ultra-pure water held in a cylindrical tank around 39 meters wide and 41 meters tall, roughly the height of a 13-story building. Buried about 1,000 meters underground, roughly 3,300 feet, in an old mine. Even with that scale, Even with that much mass sitting in the dark, you don't get a flood of neutrinos. You get a few tens of clear solar neutrino events per day, plus atmospheric ones and other sources, sitting on top of background signals you work very hard to remove. The size isn't overkill. It's just what you need so that almost never becomes often enough to do real physics. So when a neutrino finally does interact in that volume, what does it actually look like? How do you know it was there? Most of the time, the neutrino hits a nucleon or an electron and produces a charged lepton, an electron, a muon, and in rare high-energy cases, a tau. That charged lepton then shoots through the water or ice. Light in water travels slower than light in vacuum. If the lepton speed is high enough, it can move faster than light can move in that medium without ever breaking the ultimate speed limit in vacuum. When that happens, the particle emits Cherenkov radiation, a cone of blue light that spreads out along its path. It's the optical version of a sonic boom, not in sound, but in the electromagnetic field. The walls of the detector are covered with thousands of photomultiplier tubes, PMTs for short, which are insanely sensitive light sensors. Each one can pick up a handful of photons and convert them into an electrical signal. When a neutrino event happens, a pattern of PMTs fires within nanoseconds. By looking at which tubes lit up and when they lit up, scientists reconstruct the direction the lepton came from, the shape of the light cone, and the energy of the original neutrino. You never see the neutrino itself, but you see its fingerprint in that flash pattern. If water in a mine works, can you scale this up even more? Can you turn a piece of a continent into a neutrino detector? That's exactly what the IceCube Neutrino Observatory in Antarctica does. Instead of building a tank, IceCube instruments a natural one, about a cubic kilometer of very clear Antarctic ice. Engineers drilled holes down to depths between roughly 1,450 and 2,450 meters, so about 4,700 to 8,000 feet. Along 86 vertical strings, they lowered more than 5,000 digital optical modules, each one a pressure sphere with a sensitive light detector and electronics inside. Once the water refroze, those modules were locked in place in the ice. Now the ice itself is the target material. When a high-energy neutrino interacts, it produces charged particles that emit Cherenkov light in the ice, and the buried modules pick up the flashes. IceCube has seen neutrinos with energies in the peta-electron volt range. That's 1,000,000 billion electron volts, coming from outside our galaxy. These extreme events are rare. A single one can be a big deal, but they tell you that somewhere out there, cosmic accelerators like active galactic nuclei or blazars are throwing particles to energies far beyond anything the Large Hadron Collider can reach. But here's the key point. Neutrino physics is not just about one spectacular flash. Most of the real discovery work comes from counting, from patterns, from statistics. Take Super-Kamiokande again. It didn't become famous because it saw a neutrino. It became famous because it saw thousands of atmospheric neutrino events, and it noticed that muon neutrinos coming from below, which had crossed Earth before reaching the detector, were fewer than muon neutrinos coming from above. That up-down difference, after you correct for geometry and production rates, was the smoking gun for neutrino oscillations in 1998. It told us that as neutrinos travel through Earth, some of them change flavor from muon type to tau type, which the detector is less sensitive to. Solar neutrino experiments do something similar. They look at how the detection rate changes with energy, with day versus night, and with Earth's orbit. Reactor experiments track how the count rate falls off as you move detectors farther from the reactor cores. Long baseline accelerator experiments look at how many neutrinos of each flavor arrive at different energies. None of these effects are huge on their own, but every small deviation from just a random spray encodes real physics in the data. All of this only works if you can trust that a flash in the detector is what you think it is, and that's where extreme purity and isolation come in. The water in Super-Kamiokande is so pure that it will slowly dissolve metal. Dust, dissolved ions, and radioactive impurities are enemies because they create false signals. The water is constantly filtered, recirculated, and monitored so that any light you see is more likely to come from a real interaction, not from the water itself. The tank is deep underground, so that cosmic ray muons created in the atmosphere are mostly absorbed before they reach the detector, cutting down background noise by orders of magnitude. In IceCube, the overlying ice, between 1.5 and 2.5 kilometers thick, acts as a natural shield. Cosmic ray showers above create muons, but many of those are stopped in the ice before they reach the instrumented volume. The ice is dark, cold, and incredibly clear, so light can travel tens of meters without being scattered much at all. Every design choice is about making the environment as quiet as possible, both chemically and physically, so that when a neutrino finally does interact, the signal stands out. So the strategy is simple, but extreme. You surround a ghost with a huge, silent mass of matter. You watch it with the most sensitive cameras you can build, you bury everything under rock or ice to mute the outside world, and then you wait. Most of the time, nothing happens. Occasionally, you get a flash. Over years, those flashes add up to clear patterns, and out of those patterns, you extract the behavior of a particle that mostly refuses to talk to you. And that raises the next big question. If these detectors are telling us that the sun's neutrino output doesn't quite match what early theory predicted, is the problem with the star or with our understanding of the neutrinos themselves? And what do you do when an entire star suddenly looks like it might be broken according to your detectors? For a long time, the numbers coming from the sun told us something that sounded ridiculous. Either the sun was broken, or our detectors were lying, or neutrinos were doing something we didn't even have in the theory yet. Early solar neutrino experiments, especially the Homestake experiment in the US, were the first to make this obvious. Homestake was basically a huge tank of dry cleaning fluid, rich in chlorine, buried deep underground in a mine. Every now and then, a solar electron neutrino would hit a chlorine nucleus and turn it into argon. The experimenters would then literally flush the tank, extract the tiny number of argon atoms, and count them. It was slow, it was painful, and it worked. The problem was the result. The rate they measured was only about 1/3, sometimes closer to 1/2 of what standard solar models predicted. Not a small difference, a factor of 2 to 3. According to the theory, the sun's core should have been producing way more electron neutrinos than Homestake was seeing. For decades, that deficit stayed. Either the sun was somehow underproducing neutrinos, or our models of nuclear fusion in the core were wrong, or something was happening to the neutrinos on the way to Earth that nobody had accounted for. This was the missing neutrino crisis. So you had a serious tension. Extremely solid nuclear and stellar physics on one side, and carefully done experiments on the other, disagreeing by a factor of 2 to 3. The question was, which part of the chain do you blame? To answer that, you have to look at how different detectors actually see neutrinos. Homestake was a radiochemical experiment. It didn't see events in real time, it just counted how many chlorine atoms got converted to argon over weeks. It was sensitive mainly to electron neutrinos above a fairly high energy threshold. Later experiments moved to different detection methods. Detectors like Super-Kamiokande in Japan use ultra-pure water and look for Cherenkov light from electrons scattered by solar neutrinos. They see events one by one, with timing and energy information. The Sudbury Neutrino Observatory, SNO, in Canada, used heavy water, where the hydrogen is replaced by deuterium. That allowed it to detect neutrinos in 2 different ways. One interaction channel that was mostly sensitive to electron neutrinos, and another neutral current channel that was sensitive to all neutrino flavors equally. Here's what those experiments found when you put the pieces together. The total flux of neutrinos of all flavors, measured via the neutral current channel in SNO, agreed pretty well with the solar model's predictions. The sun was making about as many neutrinos as theory said it should. But the flux of electron neutrinos, measured via electron scattering channels and charged current interactions, was low. In other words, the sun was not underproducing neutrinos, it was underproducing electron neutrinos by the time they reached Earth. That pushed the blame away from broken sun and straight onto the neutrinos themselves. The radical solution was this: neutrinos were changing flavor in flight. Electron neutrinos created in the sun's core were not all arriving at Earth as electron neutrinos. Along the 8-minute trip, some of them were turning into muon neutrinos and tau neutrinos, which early detectors like Homestake were basically blind to. As soon as you allow this flavor conversion, the numbers snap into place. The total number of neutrinos stays in line with solar models, but the fraction that are still electron flavor at Earth is lower, exactly what experiments were seeing. For flavor to change over distance, neutrinos can't be exactly massless. They have to have small but non-zero masses. And the flavor states, electron, muon, tau, have to be mixtures of these mass states. That mixing is what makes oscillations possible. So the solar neutrino problem wasn't just about the sun. It was direct evidence that neutrinos have mass and mix, meaning the standard model in its original form was incomplete. Fixing the crisis meant extending the theory. There's another twist. The environment neutrinos travel through can change how strongly they oscillate. The sun itself acts like a kind of neutrino lens. In the dense core of the sun, there are a lot of electrons. Electron neutrinos interact with those electrons via the weak force in a way that muon and tau neutrinos do not. That extra interaction shifts the effective properties of the neutrinos as they move through the solar material. The result is what's called the MSW effect, after Mikheyev, Smirnov, and Wolfenstein. In simple terms, the dense matter inside the sun can enhance flavor conversion at certain energies. When experiments measure the solar neutrino rate as a function of energy, they see exactly this behavior: lower electron neutrino survival at certain energies, matching the MSW predictions. It's like getting an X-ray of the solar interior, not with photons, but with how electron neutrinos are being converted by the matter they pass through. So what started as an embarrassing mismatch turned into a precision tool. The missing neutrinos were not missing at all. They had just changed their identity on the way here. In the end, the solar neutrino problem did two big things at once. It confirmed that our basic models of how the sun shines were right, the core really is fusing hydrogen into helium at the expected rate, and it forced particle physics to accept that neutrinos have mass and mix, meaning the standard model in its original form was incomplete. Neutrinos went from being sort of massless bookkeeping fix in beta decay to being dynamic particles that morph between flavors over astronomical distances and react to matter in subtle ways that we can actually measure. Once again, the pattern was the same. Why don't we see what we expect became because nature is using a trick you haven't put into your equations yet. And that immediately leads to a deeper question. If neutrinos are changing flavor while they travel, what does that process really look like in detail? How do you describe a particle that doesn't keep a fixed identity? And what does that say about the difference between the particles that carry forces and the mass states that actually travel through space? You've seen that the sun's neutrinos arrive in the wrong flavor mix, so now you need to deal with the weird part. Neutrinos don't keep a fixed identity while they travel. You can label a neutrino in two ways. One way is by flavor: electron, muon, or tau. That's how it shows up in weak interactions, which charge lepton it's paired with when it's created or absorbed. The other way is by mass. There are 3 mass states, each with a slightly different mass. Here's the catch. Those two sets of labels are not lined up. The flavor states are not the same thing as the mass states. They're mixtures. So when a neutrino is born as a pure electron flavor in the sun's core, what actually leaves the core is a quantum combination of 3 different mass states. Each mass state has almost the same energy, but not exactly. And because their masses differ slightly, they move forward with slightly different phase as they propagate. Over distance, those tiny differences in phase add up. The quantum pieces that started off in sync start to drift relative to each other. When you ask, what flavor is this neutrino now, you are basically asking how those mass components add back together at that point in space. Sometimes they recombine mostly as electron flavor again, sometimes mostly as muon or tau, sometimes as a mix. That continuous remixing is what we call oscillation. In practice, the chance that a neutrino flips from one flavor to another depends on a few key things: the distance it has traveled, the energy it has, the mixing angles that tell you how strongly flavors and masses are mixed, and the differences between the squares of the masses, not just the masses themselves. There's a characteristic distance scale in the problem, the oscillation length, the distance over which the flavor mix completes one full cycle and returns to where it started. That length grows if you increase the neutrino's energy, and shrinks if the mass squared differences are bigger. If you plug in typical numbers with energy in the millions of electron volts and mass squared differences in the tiny ranges that experiments have measured, the oscillation lengths come out in real-world units like meters, kilometers, tens of kilometers, or hundreds of kilometers, depending on the energy. That's why reactor experiments put their near and far detectors at specific distances of about 1 to 2 kilometers, then 20 to 60 kilometers. That's why long baseline accelerator experiments put their far detectors hundreds of kilometers away. They're not random placements. They are tuned to sit near where the oscillation effect is largest for the energies they are using, so the disappearance or appearance of a given flavor is as strong as possible. You don't have to rely only on the sun and reactors to see this. The atmosphere gives you a big, free oscillation experiment that runs all the time. High-energy cosmic rays slam into the upper atmosphere and make showers of particles, including pions and kaons. Those unstable particles decay, producing muons and neutrinos, mainly muon neutrinos, plus some electron neutrinos. So above your head and below your feet, there's a constant flux of atmospheric neutrinos coming from all directions. A detector like Super-Kamiokande can see a lot of those events over time. Here's what they did. They counted how many muon neutrinos arrived from above, meaning they had traveled maybe tens of kilometers through the atmosphere, and how many arrived from below, meaning they had to cross Earth, about 13,000 kilometers, about 8,000 miles, before hitting the detector. That downgoing flux matched expectations pretty well. The upgoing muon neutrino flux was clearly lower. At the same time, the data showed signs of tau neutrinos appearing that hadn't been there at creation. The simplest way to explain that is oscillation. As muon neutrinos travel a short distance from above, they don't have time to change flavor much. As they travel the long path through Earth from below, they do. Muon flavor gets converted into tau flavor along that path. That up-down difference, when nothing else about the production process or geometry should favor one direction over the other, was a clean and very robust sign that neutrinos change identity in flight. That result, along with others, was strong enough to earn a Nobel Prize. After that, the next logical step was to build controlled versions of this, using beams you can switch on and off. In experiments like T2K in Japan, proton beams from an accelerator hit a target at Tokai, creating pions that decay into muon neutrinos. The beam is aimed through Earth at a detector in Kamioka, about 295 kilometers away, a bit over 180 miles. In NOVA in the US, the beam runs from Fermilab in Illinois to a detector in Minnesota, roughly 800 kilometers away, about 500 miles. In both cases, you start with a beam that's mostly muon neutrinos, you measure what you have close to the source with a near detector, then you measure what you get at the far detector. What they see is two things. First, a deficit of muon neutrinos at specific energies compared to what you'd expect if they didn't oscillate. That's disappearance. Second, a non-zero number of electron neutrinos turning up at the far detector even though you didn't start with many. That's appearance. When you plot the event rate as a function of energy, you see wavy patterns, dips, and peaks, exactly where the oscillation framework says they should be for the known distances. By comparing neutrino beams and antineutrino beams, you can also start to look for differences between the two, possible signs of CP violation in the neutrino sector, which ties into the matter-antimatter story later on. So, step back and summarize what this means for the particle itself. A neutrino is not born an electron neutrino, travels as an electron neutrino, and dies as an electron neutrino. That's the old, simple picture, and it's wrong. The more accurate picture is a neutrino is created in a definite flavor state, because that's how the weak interaction works at the source. But the thing that actually propagates through space is a mixture of three mass states, each with its own slightly different mass and phase evolution. As it travels through rock, air, ice, your body, those components slip out of sync. When the neutrino finally interacts again, the flavor you measure is the result of how those mass components combine at that point. You can get the same overall neutrino becoming a different flavor, just because it had enough space and time for the phases to spread out and interfere in a new way. That identity shift is not rare, it is constant. It's happening to solar neutrinos on the way from the core to Earth, to atmospheric neutrinos going up and down through the planet, to reactor neutrinos as they move from core to detector, and high-energy cosmic neutrinos crossing intergalactic space. The neutrino is a shapeshifter by default. That behavior is built into nature, and it only makes sense if neutrinos have mass and if flavor and mass are misaligned in a very specific way. And that immediately leads to the next big problem. Neutrinos prove they have mass, and they tell you the differences between those masses, but they don't tell you how heavy the neutrinos actually are, or how those masses are ordered. So the question becomes, how do you weigh a particle that never stops, and how do you get an absolute mass for something that refuses to sit on the scale and almost never hits anything? Oscillations already told you neutrinos have mass, so here's the annoying part. We still don't know how heavy they actually are. How do you weigh a particle that never sits on the scale and almost never hits anything? From oscillation experiments, you get very specific information, but it's incomplete. By watching flavors change with distance and energy, you can measure the differences between the squares of the masses of the three neutrino types. You get numbers like the second mass state is separated from the first by about 7.5 times 10 to the minus fifth electron volt squared, and the third is separated from one of them by about 2.5 times 10 to the minus third electron volt squared. Those are solid. They come from many independent experiments. But those values only tell you the spacing between the rungs on the ladder, not how high the ladder is above the floor. You know the gaps between the masses, you don't know the absolute mass of any of them. On top of that, you don't know if you have a normal ordering, 2 lighter masses and 1 heavier, or an inverted ordering, 2 heavier ones and 1 lighter. Oscillations alone can't tell you where the whole set sits on the mass axis, or which pattern nature picked. So you know neutrinos are not massless, you just don't know exactly how heavy they actually are, or how the 3 values are arranged. So the next question is obvious. If oscillations can't give you the absolute mass, who can? How do you actually measure a number that small in the lab? One of the most direct approaches is the Katrin experiment in Germany. Instead of trying to catch neutrinos and weigh them, Katrin looks at the electrons that come out of a simple nuclear decay, tritium beta decay. In that decay, a tritium nucleus turns into helium, emits an electron, and emits an electron antineutrino. If the neutrino had exactly 0 mass, the electron spectrum would have a sharp cutoff at a specific maximum energy. If the neutrino has a tiny mass, that cutoff gets slightly rounded and shifted. So Katrin builds a gigantic, extremely precise spectrometer, takes a ridiculous number of beta decay events, and zooms in on just the last tiny fraction of the energy spectrum near that endpoint. It measures that shape with insane precision. Any non-zero neutrino mass leaves a faint imprint in that tail. By not seeing a big distortion, Katrin sets an upper limit. Right now, that limit is under 0.45 electron volts squared for the effective electron antineutrino mass with high confidence. That's less than a millionth of the electron's mass. If you like rough analogies, if the electron was the mass of a typical car, the neutrino would be lighter than a snowflake landing on the roof. Katrin hasn't pinned down the exact mass yet, but it has chopped off a huge part of the possible range. It tells you that neutrinos are ridiculously light and pushes the maximum allowed value lower every time it improves its sensitivity. But lab experiments aren't the only scales available. The entire universe acts like a kind of neutrino mass detector too. In the early universe, neutrinos were moving at nearly the speed of light and behaved like radiation. As the universe expanded and cooled, their tiny masses started to matter, and they began to act more like very light matter. This shift influences how structures grow. Neutrinos that stay fast for a long time tend to wash out small-scale clumps because they stream out of overdense regions instead of getting trapped. If neutrinos were too heavy overall, they'd slow down earlier and suppress the formation of small galaxies and fine-grained structure more strongly than we actually see. By comparing detailed maps of the cosmic microwave background with large-scale galaxy surveys and gravitational lensing measurements, cosmologists can fit models where the total mass of all three neutrinos is one of the parameters. The data push that total down to something like a few tenths of an electron volt at most. In many analyses, more like under about 0.1 to 0.2 electron volts. That is consistent with what Katrin is seeing, and in some cases even tighter. So structures hundreds of millions of light years across are quietly telling you how much a particle weighing far less than an electron can weigh, because that weight changes how cosmic web filaments and galaxy clusters form. So now you have two independent lines of attack: precision beta decay on Earth and precision cosmology on the sky, both converging on the same conclusion. Neutrinos are incredibly light, but not weightless. Why is that such a headache for theory? In the original Standard Model, neutrinos were simply set to have zero mass. There were no right-handed neutrino fields in the theory, and no straightforward way to hook neutrinos up to the Higgs mechanism the way we do for electrons, quarks, and other fermions. So a strictly massless neutrino fit very nicely into that framework. The moment experiments showed neutrinos oscillate and therefore have mass, that neat picture broke. To fix it, you have to extend the model. One option is to introduce right-handed neutrinos and give them ordinary Dirac masses via the Higgs, like other particles. Another, more popular in many theories, is to assume neutrinos are Majorana particles, meaning each neutrino is its own antiparticle, and to introduce huge mass terms for these mostly sterile partners. Through something called the seesaw mechanism, you can make the neutrinos we see extremely light, while their invisible partners are extremely heavy, possibly near the grand unification scale, far beyond what any collider will ever reach. The key point is this: the tiny neutrino masses we infer in experiments are not trivial to generate. They almost demand new physics at very high energy scales. So every time you shrink the allowed range of neutrino mass, you are not just adjusting a number, you are tightening the constraints on what that new physics can look like. This is why people care about shaving off more digits from the neutrino mass limits. Every improvement from Katrin, every better cosmological fit, closes off whole families of speculative models and nudges others into focus. You're using a barely interacting, almost weightless particle to probe energy scales and mechanisms that are otherwise completely out of reach. So when you look up at the large-scale structure of the universe, the pattern of galaxies and voids, and when you look down at a graph of electron energies from tritium decay in a lab, you're seeing two ends of the same story. Both are quietly telling you how much neutrinos can weigh, and both are signaling that our current best theory of particles is missing a piece. And that raises the next question. If neutrinos were already playing this role in the early universe, affecting the expansion rate and structure growth, what exactly were they doing in those first seconds after the Big Bang? And how do relic neutrinos from that era still shape the cosmos you live in now? Right after the Big Bang, neutrinos weren't rare ghosts. They were just part of the crowd, smashed into everything else so often that they were basically glued into the hot plasma. In the first second, the universe was a dense mix of photons, electrons, positrons, neutrinos, antineutrinos, and a few protons and neutrons, all in thermal equilibrium. Temperatures were around 1 billion to 10 billion Kelvin. At those energies, neutrinos were interacting all the time through the weak force. They were created and destroyed so fast that their energy distribution matched everything else. As the universe expanded, it cooled. When the temperature dropped to around 1 mega-electron volt, roughly 1 trillion Kelvin, the interaction rate of neutrinos fell below the expansion rate. In plain language, space was stretching faster than neutrinos could keep up their collisions. At that point, they effectively decoupled. They stopped interacting frequently, and from then on, they just streamed freely through space, carrying the energy distribution they had at that moment, only gradually cooled by the expansion itself. That decoupled neutrino bath should still be here today. When you run the numbers, you get a number density of around a few hundred relic neutrinos per cubic centimeter. That's a few hundred in every cubic centimeter of the room you're in, per flavor family. just at very low energies and very low temperatures, around 2 Kelvin, slightly colder than the cosmic microwave background. We haven't directly detected that background yet, but those existents are locked into the same calculations that correctly predict the microwave background and the light element abundances. You can't get a consistent early universe story without them. A few minutes after decoupling, another key process kicked in: primordial nucleosynthesis, the first real nuclear chemistry in the universe. Protons and neutrons started assembling into light nuclei, mainly helium-4, plus some deuterium, helium-3, and trace lithium-7. The final mix of those elements depends very sensitively on how fast the universe was expanding during those first minutes. And what sets that expansion rate, besides gravity itself? The total energy density in relativistic particles, including neutrinos. If you change the number of light particle species or change how neutrinos behave at those times, you change the expansion speed. Expand faster and neutrons freeze out differently. Less time for some reactions, different end ratios. Expand slower and you get a different pattern again. When we compare the predicted abundances of helium and deuterium with what we actually observe in old gas clouds and in the oldest stars, they line up when we include about 3 kinds of neutrinos with standard properties. If you try to add a bunch of extra light species or make neutrinos interact in very non-standard ways, the whole pattern falls apart. So those early nuclear ashes, helium and deuterium, are acting as a probe of neutrino physics. They're telling you, whatever neutrinos were doing in the first few minutes, it has to look very close to the standard picture. Fast forward to about 380,000 years after the Big Bang, when the cosmic microwave background was released. Photons finally decoupled from matter when electrons combined with protons to form neutral hydrogen, and light could travel long distances without constantly bouncing off free charges. The CMB we see today at about 2.7 Kelvin is that fossil light. But even there, neutrinos left fingerprints. Before recombination, the plasma of photons and baryons, protons and neutrons, was oscillating, forming sound waves in the early universe. These oscillations show up as peaks in the power spectrum of the CMB temperature fluctuations. Specific scales where hot and cold spots are more pronounced. Free-streaming neutrinos, already decoupled by then, affect those oscillations. They change the phases and amplitudes of the peaks in very specific ways because they add extra radiation that doesn't get dragged around by the plasma in the same way photons do. Satellites that map the CMB with high precision, like WMAP and Planck, measure those peaks in detail. When cosmologists fit their models to that data, one of the parameters they extract is the effective number of neutrino-like species, usually written as NF. The best fits cluster around the value very close to 3, which is exactly what you expect for 3 light neutrino flavors with standard behavior. If there were a lot of extra light particles or if neutrinos were tightly coupled to something else at that epoch, the pattern of peaks would shift. It doesn't. So that's another independent check that the basic neutrino story is right. Now add in the fact that neutrinos don't stay purely radiation forever. Because they have mass, even if it's tiny, they eventually slow down as the universe cools and start to contribute to the matter budget instead of just the radiation budget. This switch happens gradually, and it affects the growth of structure. When neutrinos are still fast, they don't like to sit in small gravitational wells. They tend to stream out of overdense regions rather than clustering. That behavior suppresses the formation of small-scale structure, like small galaxies and fine details in the cosmic web. Larger structures, like massive clusters, are less affected. The exact scale at which this suppression kicks in depends on the neutrino masses. Higher total neutrino mass means a stronger suppression of small structures. By looking at galaxy surveys, gravitational lensing maps, and other tracers of structure across hundreds of millions of light years, and by comparing them to simulations that include different neutrino mass sums, cosmologists can constrain how much mass neutrinos can collectively carry. That's how you get those bounds on the sum of neutrino masses being below a few tenths of an electron volt. It's the same story you heard earlier, but now you can see the logic. Ghost particles passing through everything are still heavy enough in total to change which galaxies form and which ones never make it. So why does any of this matter for the question you started with? Why neutrinos pass through everything. Because the same property that makes neutrinos so hard to detect locally, their almost non-existent interaction strength, is exactly what lets relic neutrinos keep such clean information from the earliest times. Photons were trapped in the plasma for hundreds of thousands of years, constantly scattered, absorbed, and re-emitted before they could travel freely. Neutrinos checked out after less than a second and never really came back into equilibrium. They have been traveling across the universe almost undisturbed ever since. That means if you could detect the cosmic neutrino background directly, you'd be reading a message from the first second of the universe, carried by particles that have essentially ignored everything in between, including all the galaxies, clusters, stars, and you. Even without direct detection, the indirect evidence in the CMB and in nucleosynthesis tells you they are there, still moving through you right now, unchanged in their basic distribution for billions of years, except for the redshift from cosmic expansion. So the passes through everything behavior is not just a quirky detail. It's what makes neutrinos the cleanest possible witnesses of the early universe. They don't get scrambled the way light does. They don't get trapped in plasma. They just leave, and they keep going. That sets up the next step, because if neutrinos can carry pristine information from the first second, they can also carry sharp signals from violent events much later on, like supernovae and active black holes, cutting straight through matter and magnetic fields that block or bend everything else. The question is, what are those cosmic neutrinos telling you about the most extreme engines in the universe? And how do we read those signals when a single detected particle might have traveled for billions of years to reach one sensor buried in ice or water? A star can explode on the other side of a galaxy, and the first warning you get is not light. It's a burst of neutrinos slamming straight through you before any telescope sees a thing. That's exactly what happened with supernova 87A. When its core collapsed, deep inside its envelope, photons were trapped, bouncing around in dense matter. Neutrinos were not. In a core collapse, almost all of the gravitational energy, something like 10 to the 46 joules, comes out as neutrinos over about 10 seconds. They stream straight out of the forming neutron star, through the star's outer layers and into space. On Earth, several underground detectors were running at the time. They saw a cluster of about 20 dozen neutrino events, arriving within roughly 13 seconds, a few hours before the visible supernova lit up the sky. The energies and timing of those neutrinos matched the models of a core collapsing, forming a neutron star and cooling by dumping energy into neutrinos. That tiny set of events, just a few dozen flashes in tanks of water and cleaning fluid, was enough to confirm that neutrinos are the main energy channel in a core collapse supernova, and that they can escape from regions completely opaque to light. If a similar supernova went off today inside our own Milky Way, the story would be different in scale. Detectors like Super-Kamiokande, IceCube, and others would see thousands to millions of neutrino events in a burst lasting around 10 seconds. You'd get time structure, energy evolution, maybe even signatures of the neutron star forming, possibly collapsing further into a black hole. And all of that would arrive before the envelope becomes transparent enough for photons to escape. Telescopes would be late to their own show. The neutrino detectors would already have a frame-by-frame record of the core's death. That's one side of cosmic neutrinos, brief, intense bursts from individual explosions. The other side is a steady, faint rain of ultra-high energy neutrinos from far beyond our galaxy. IceCube has been watching the Antarctic ice for years now. On top of the expected background of atmospheric neutrinos, it sees a population of events with energies from tens of tera-electron volts up into the peta-electron volt range. That's 10 trillion to a million billion electron volts, way beyond what you get from most natural processes in the atmosphere. Their arrival directions are roughly spread across the sky, not concentrated along the horizon the way many atmospheric backgrounds are. Their energy spectrum doesn't match what you'd expect if they were just produced by cosmic ray showers in the atmosphere. The simplest interpretation is that these are astrophysical neutrinos, made in cosmic accelerators like active galactic nuclei, starburst galaxies, or other extreme environments. In one famous case, a very high-energy IceCube event, nicknamed something dramatic because of its energy, pointed back, within uncertainties, toward a flaring blazar, a galaxy where a supermassive black hole is shooting a jet roughly in our direction. Around the time of the neutrino, gamma-ray telescopes saw that blazar brighten. It's not a 100% clean smoking gun, but it's strong evidence that at least some of the high-energy neutrino flux is coming from jets around supermassive black holes. That's neutrino astronomy in action, using a single particle to tag a specific engine in a distant galaxy. To see why neutrinos are so valuable here, compare them with the other messengers we use, cosmic rays and gamma rays. Cosmic rays are mostly protons and nuclei. They're charged, so they get bent and scrambled by magnetic fields in galaxies and in intergalactic space. By the time a cosmic ray reaches you, its arrival direction is badly distorted, and it no longer points back cleanly to where it came from. Gamma rays, high-energy photons, travel in straight lines, but they can be absorbed or scattered by dust, gas, and by low-energy background photons, like the infrared and microwave backgrounds. Very high-energy gamma rays can be attenuated over cosmological distances, wiped out by interactions before they get here. Neutrinos have neither problem. They're neutral, so they ignore magnetic fields and fly in straight lines. They barely interact, so most of them are not absorbed by gas, dust, or radiation fields, even near dense sources like black holes or inside starburst regions. That means when a high-energy neutrino hits a detector on Earth, its direction is, within some angular uncertainty, still pointing back toward its source. It's the only messenger that can come straight out of places where everything else is absorbed, scattered, or bent beyond recognition. At high energies, you can even use Earth itself as part of the instrument. A neutrino arriving from below your detector, coming from the opposite side of the planet, has had to pass through Earth's interior first. For low energies, that's not a big deal. Earth is mostly transparent. For very high energies, the interaction probability rises, and a significant fraction of those upgoing neutrinos get absorbed. So, if you plot how many high-energy neutrino events you see as a function of zenith angle, essentially from above versus from below, and as a function of energy, you see the pattern change. Downgoing events are less affected, upgoing ones get eaten away as energy rises. By fitting those angular and energy distributions, IceCube and similar experiments can measure the neutrino cross-section at energies far beyond any lab can reach, and confirm that the interaction strength grows with energy the way the theory predicts. The same angle dependence also helps separate real neutrinos from misidentified atmospheric muons, because muons can't easily cross the whole planet, but neutrinos can. When you put it all together, each individual PeV scale neutrino event is a very sharp, very strange message. One particle made in an extreme environment maybe billions of light years away travels almost entirely unbothered across the cosmic web, through filaments of galaxies and huge voids, through whatever gas and dust lie along the line of sight, through the entire thickness of Earth, and finally hits a single proton or electron in a few cubic meters of ice or water. That one interaction makes a cone of Cherenkov light, a cluster of photomultiplier hits, a line in a data file. From that, you reconstruct a direction, an energy, and a rough idea of what kind of process had to accelerate particles to those energies. You're seeing shock waves where jets slam into surrounding material, magnetic reconnection near black hole disks, or violent outflows in merging galaxies. Passes through everything turns out to be exactly what you want if your goal is to get undistorted information out of the harshest possible environments. But there's an even deeper twist waiting. These ghost messengers don't just tell you about explosions and black holes. The difference between neutrinos and antineutrinos and the way they might break certain symmetries could be the reason there's any matter at all for stars and black holes to exist in the first place. So, the next question is, can these almost massless, almost non-interacting particles be responsible for the biggest imbalance in the universe? The fact that matter won over antimatter instead of everything annihilating into pure radiation. Right now, you're living in a universe that clearly prefers matter over antimatter, and that's not what the basic Big Bang recipe says should have happened. If you roll the clock back, the hot early universe should have created particles and antiparticles in almost equal amounts. For every proton, an antiproton. For every electron, a positron. Bring those together and they annihilate into radiation. If everything were perfectly symmetric, you wouldn't be here. You'd just have a smooth bath of photons and neutrinos. No atoms, no stars, no planets, no you. So, there has to be a bias built into the laws of physics, something that lets matter win by a tiny margin. That bias has to tick a few boxes. You need reactions that treat matter and antimatter slightly differently. That's called CP violation, combining charge conjugation, swap particles with antiparticles, and parity, flip left and right. You need conditions out of equilibrium, so reactions don't just run forwards and backwards in the same way. And you need processes that create or destroy baryon number or lepton number. Put all that together at the right time, and you can end up with a tiny excess of matter that survives after almost everything else annihilates. That leftover sliver is literally the stuff you're made of. One cleanest idea for how to do this puts neutrinos right in the middle. It's called leptogenesis. The picture goes like this. At some very early time, when temperatures and energies were far beyond anything we can reach in a collider, there were heavy right-handed neutrinos, much heavier than the neutrinos we see today. These heavy neutrinos were unstable. As they decayed, they produced leptons and antileptons, but if CP symmetry is slightly violated in those decays, the rates are not exactly equal. You end up with a tiny excess of leptons over antileptons. Then, the standard model has its own set of processes, sphalerons, that can convert some of that lepton asymmetry into a baryon asymmetry, basically turning a lepton imbalance into a proton and neutron imbalance. When the universe cools and annihilations finish, that small leftover baryon excess is what becomes all the matter you see. In that story, the same mechanism that gives light neutrinos their tiny mass through a seesaw involving ultra-heavy partners also sets the size of the matter-antimatter imbalance. Neutrinos go from weird ghost particles to the reason there is anything instead of just light. We don't have direct experimental evidence for leptogenesis yet. Those heavy neutrinos, if they exist, are probably way out of reach in energy. But you can look for indirect clues, and one of the main ones is CP violation in the neutrinos we can study. That's why long baseline oscillation experiments care so much about whether neutrinos and antineutrinos behave differently. In setups like T2K and NOVA, you can run the accelerator in neutrino mode, producing a beam dominated by muon neutrinos, and then in antineutrino mode, producing mainly muon antineutrinos. In both cases, you measure how many muon-type particles disappear and how many electron-type appear at the far detector. If the universe treated neutrinos and antineutrinos perfectly symmetrically in these oscillations, the conversion rate as a function of energy and distance would match once you correct for obvious differences like cross-sections. But if there is CP violation in the lepton sector, the pattern of appearance and disappearance will be slightly different for neutrinos versus antineutrinos. Early data from T2K and NOVA have shown hints that neutrinos might oscillate into electron flavor at a different rate than antineutrinos do, but the statistics are not strong enough yet to call it a discovery. Future experiments like DUNE and Hyper-Kamiokande are designed to push this much further. If they find a clear, large CP violating effect, it would be a huge boost for leptogenesis-style explanations. There's another even more fundamental question sitting under all of this. What exactly is the relationship between neutrinos and antineutrinos? Are they genuinely different particles like electrons and positrons, or are they actually the same thing under the hood? If neutrinos and antineutrinos are distinct, we call them Dirac particles, like most of the fermions in the standard model. If they are actually the same particle just seen in different helicity states, they're called Majorana particles. That difference matters because if neutrinos are Majorana, lepton number, the rule that says number of leptons minus antileptons stays constant, can be violated in special processes. That's exactly what many leptogenesis models need. The main handle on this is something called neutrinoless double beta decay. In normal double beta decay, a nucleus emits 2 electrons and 2 antineutrinos. If neutrinos are Majorana, under the right conditions, you can have a process where the 2 antineutrinos basically cancel each other out internally, and you only see the 2 electrons in the final state, no neutrinos escaping. That would violate lepton number by 2 units. Detecting that would tell you neutrinos are their own antiparticles. Experiments hunting for neutrino-less double beta decay bury tons of special isotopes deep underground, cool them, shield them, and wait for a very specific energy signature, where the sum of the two electron energies hits a sharp line. So far, no confirmed signal. Every no result tightens the limits on how often this process can happen, which pushes constraints on Majorana mass terms and on many versions of the seesaw. But the search is very much alive, because a single clear event could rewrite an entire chapter of particle physics. If you connect all these threads, you get a pretty wild picture. The particles that mostly ignore you, that cross Earth and your body as if you're not there, might be the ones that gave the universe its matter in the first place. If neutrinos are Majorana, if they have CP-violating behavior and oscillations, and if their tiny masses come from some very high-scale physics, then they become agents of cosmic bias. They tip the scales in favor of matter over antimatter by just enough that atoms, stars, galaxies, and life could exist, instead of everything blinking out into radiation. So, passes through everything is only half the story. The other half is decided whether there would be anything to pass through. These almost invisible particles could have set the initial conditions for the entire visible universe. And that leads to a very practical question. If neutrinos can tell you about something as deep as why matter exists at all, what can you do with them closer to home? Can you actually use these ghosts as tools to scan things you can't touch, like the inside of Earth or the core of the sun? You've seen neutrinos as messengers from the early universe and from supernovas, so here's the next step. Can you actually use them as tools to scan things you can't touch, like the inside of Earth or the core of the sun? Start with Earth. Every high-energy neutrino that comes through the planet has a small chance of being absorbed or scattered, and that chance depends on its energy and how much dense material it travels through. A neutrino that skims just under the crust crosses a shorter, lighter path than one that comes straight up from the opposite side of the planet, through the core. If you measure the flux of neutrinos from many directions and many energies, you don't just see some events, you see how the planet has filtered them. In principle, you can turn that around. If you know the incoming flux and you know the interaction physics, you can work backwards from the angle-dependent deficit of neutrinos to reconstruct the density profile inside Earth. That's neutrino tomography. We already use seismic waves from earthquakes to map the core and mantle boundaries, but high-energy atmospheric neutrinos have started to give an independent check, showing evidence of the presence of a dense core and a less dense mantle just from how often neutrinos make it through along different paths. The resolution right now is crude, but the fact that it works at all proves the concept. You can use particles that almost never interact to verify the structure of an entire planet. If you can read Earth's interior with neutrinos, can you also use them to watch something human-made, like a reactor, from outside its shielding? Reactors are intense anti-neutrino sources, and concrete, rock, and steel hardly matter to those anti-neutrinos. That means you can put a comparatively small detector, maybe a few tons of scintillator, tens of meters away from a reactor core, not necessarily in the same hall, and still pick up a clear signal. The rate of detected antineutrinos tracks the reactor's thermal power, so if the power level changes, your neutrino count changes. The shape of the energy spectrum carries information about which isotopes are fissioning, uranium versus plutonium mixes, for example. So in principle, you get something like a smart meter that works through walls. You can see if a reactor has turned on or off, ramped up or down, and even whether its fuel is changing, just by watching neutrinos that don't care about security doors, shielding, or line of sight. That's why there's serious interest in neutrino detectors as tools for non-proliferation and reactor monitoring. It's not science fiction, it's already been demonstrated at research reactors. The challenge is just to make the detectors smaller, cheaper, and more robust enough for routine use. On a much larger scale, you can ask a more dramatic question. If neutrinos can come straight out of dense places, can they let you monitor the heart of the sun in almost real time? Photons made in the solar core take hundreds of thousands of years to fight their way out through the radiative zone and convective layers. Neutrinos leave the core in seconds, so if the fusion rate in the sun's core changed today, the neutrino flux at Earth would react within about 8 minutes, while the sunlight you see would still be carrying information from the older state of the core. Right now, solar neutrino experiments don't see large, rapid changes in flux. The sun is very stable over human timescales, but in principle, neutrino measurements already give you a direct readout of which fusion chains are operating, how much comes from the proton-proton chain versus the CNO cycle, and they are sensitive to details like the metallicity and mixing in the solar interior. Whenever detectors improve, you can sharpen that into something closer to real-time solar core diagnostics using neutrinos to probe conditions you'll never reach with any instrument or spacecraft. Once you accept that, it's natural to push the idea outward. Could you, in theory, use neutrinos to scan other planets, moons, or even stars? If you had a very intense, aimed neutrino beam and a sensitive detector on the other side, you could fire the beam through a planet and watch how it's attenuated at different angles. Just like with Earth, the amount of filtering depends on the density structure along the beam path. Map the attenuation pattern in detail, and you'd get the planet's internal density profile without drilling a single meter. In practice, our current neutrino sources are nowhere near powerful enough for that over interplanetary distances, and our detectors aren't big enough to compensate. But conceptually, nothing stops it except engineering. Even without artificial beams, natural sources are already doing low-resolution scans. Every upgoing atmospheric neutrino your detector records has traveled through a particular chord of Earth, and the survival probability encodes information about the density across. Solar and supernova neutrinos do the same for the stars they come from and for the material they pass through on the way to us. With enough events and big enough detectors, you can turn that into genuine tomography. The core idea tying all of this together is simple and slightly unsettling. Neutrinos let you see without touching. You can't insert a probe into Earth's core, you can't bounce light off the sun's center, you can't drill into a working reactor, and you definitely can't send a physical instrument into the environment a few kilometers above a black hole's event horizon. But you can detect neutrinos that have passed through those regions. They interact so rarely that they don't disrupt what they're probing, and they don't get scrabbled on the way out. The tiny fraction that does interact in your detector is the entire signal. It's the same idea as a CT scan, where you reconstruct internal structure from how something is attenuated, but scaled up to planetary and stellar sizes, and using particles that barely acknowledge the matter they're passing through. So you end up with this strange tool, a particle that almost always ignores you, that you can barely detect, but that quietly carries detailed information from places you will never reach. And that raises a very grounded question. If neutrinos can act as scanners and messengers on these scales, what are they doing right under your feet, around your reactors, and in underground labs? And how close are we to turning this ghostly behavior into actual infrastructure that runs in the background of civilization? Right now, under your feet, there are labs quietly watching reactors and listening to Earth's interior using particles that everyone else ignores. Take the big reactor anti-neutrino experiments first. Setups like Daya Bay in China, Reno in Korea, and Double Choose in France all did the same core trick. They put at least 2 detectors at different distances from reactor cores, one near detector, maybe a few hundred meters away, and one or more far detectors at distances of about 1 to 2 kilometers, around half a mile to a mile. Both sets of detectors see huge numbers of electron antineutrinos from the cores, but the far detectors see slightly fewer than you'd expect if neutrinos just stayed electron type the whole way. By comparing near and far rates and energy spectra very precisely, they measured how much the flux drops with distance and how that drop depends on energy. From that, they pinned down one of the key mixing angles in the neutrino sector, usually called theta 1,3. In plain language, that angle tells you how strongly electron flavor is mixed with the third mass state. A bigger angle means more probability that an electron antineutrino will turn into a different flavor over a given distance and energy. These reactor experiments nailed that number. They also ran into something weird, the reactor antineutrino anomaly. When theorists updated their predictions for how many antineutrinos reactors should produce at different energies, the experiments saw a small but persistent deficit compared to those new predictions, a few percent low. That mismatch could mean the flux calculations are off. Maybe the nuclear physics of fission products is more complicated than expected. Or in more exotic models, it could hint at additional sterile neutrino states that don't interact through the weak force at all, only mixing in through oscillations. Right now, it's unresolved. It might be nothing more than complicated reactor fuel behavior, or it might be an early sign of another layer to neutrino physics. The same detectors and others, like Camland in Japan and Borictino in Italy, have also turned their attention below, to geoneutrinos, the antineutrinos from Earth's own radioactive elements. Uranium, thorium, and potassium in the crust and mantle are constantly decaying, and many of those decays emit antineutrinos. These geoneutrinos usually have lower energies than typical reactor antineutrinos, and they arrive from below rather than the direction of nearby power plants. By separating events based on energy and, when possible, by direction, experiments can disentangle the reactor antineutrino signal from the geoneutrino signal. The number of geoneutrinos they see tells you how much radioactive decay is happening inside Earth. When you combine that with models of element distribution in the mantle and crust, you get an estimate for how much of Earth's internal heat, about 40 to 50 terawatts in total, comes from radioactivity. Current data suggests that something like half of the heat budget may be radiogenic. That links neutrinos directly to plate tectonics, to volcanic activity, and to how fast the planet is cooling down over geological time. You're literally using barely interacting particles to do energy accounting for an entire planet. All of this is happening in places you almost never think about, underground labs buried under mountains or kilometers of rock. The reason is simple. The sky is constantly raining down cosmic rays, and those rays make showers of particles, including muons, that punch through buildings and even some rock. At the surface, the rate of those background events is huge compared to the delicate neutrino signals you're trying to see. So experiments move deep underground, hundreds to thousands of meters down, sometimes more than a kilometer, over 3,000 feet. The rock above acts as a shield, absorbing most of the cosmic ray muons before they hit the detector. That doesn't eliminate background, but it cuts it down by orders of magnitude. Under your feet, in old mines and mountain tunnels, we've built some of the quietest places on Earth, not for silence in the human sense, but for silence in the particle sense. In that engineered quiet, a few extra flashes in a tank of liquid can stand out as real neutrino events instead of being drowned in noise. Once you realize neutrinos ignore shielding and distance, you start thinking about more direct applications. Could you actually send messages with them? In principle, yes, because neutrinos barely notice matter, a beam of them can go straight through Earth. People have proposed using intense accelerator-based neutrino beams to communicate with submerged submarines or even with spacecraft on the far side of the sun, where radio waves would be blocked or distorted. In 2012, one demonstration experiment encoded a simple message, basically a short word in an on-off pattern of a neutrino beam sent through about 240 meters of rock, around 800 feet. A detector on the other side read out the pattern and decoded the message. Right now, this is wildly inefficient. You need a huge accelerator, massive detectors, and you only send a tiny number of bits per second. It's nowhere near practical for everyday communication. But as a proof of principle, it matters. It shows that in extreme cases where you absolutely need a channel that ignores obstacles and interference, neutrinos can do the job. It's like discovering that you can shout through a mountain if you're willing to spend insane amounts of energy per syllable. Put all of this together, and neutrinos stop looking like a niche curiosity. They're already integrated into how we study reactors, how we measure Earth's radiogenic heat, and how we test for new physics in underground labs. They might end up as tools for ultra-secure, obstruction-proof communication in very specialized situations. So these particles that pass through everything are quietly becoming part of an invisible infrastructure layer. They penetrate shielding you build for other things. They leak out of reactors no matter what you do. They stream from the ground beneath you and from the sky above. We're only just starting to learn how to read and use that constant flow. Up to now, we've mostly built detectors that are just barely big and clean enough to see them. The obvious next move is to ask, what happens if you scale this up hard? Build detectors that are bigger by factors of 5 or 10, cleaner, sharper, wired directly into powerful beams. How much more can you wring out of a particle that barely interacts? And what new cracks in our theories will show up when you start collecting not thousands, but millions and billions of events? Right now, people are pouring money, steel, and insane engineering into one basic idea. If you build bigger, cleaner, sharper neutrino machines, the universe will have to tell you more of its secrets. In Japan, they're scaling up the Super-Kamiokande idea into something much more extreme, Hyper-Kamiokande. Super K holds around 50,000 tons of water. Hyper K is designed for about 260,000 tons of ultra-pure water, roughly 5 times the volume, in a cavern hundreds of meters underground. Think of a tank so big you could drop a skyscraper on its side inside it and still have space around it. The walls will be lined with something like 40,000 huge photomultiplier tubes, each one watching for a handful of photons from Cherenkov flashes. What does that buy you besides bragging rights? First, way more neutrino events. Solar neutrinos, atmospheric neutrinos, reactor neutrinos, accelerator beams, all of them will hit that target in bigger numbers. That means sharper measurements of oscillation parameters, better sensitivity to CP violation, and much more power to see tiny deviations from the standard model. Second, Hyper-K will be a monster supernova detector. A core collapse supernova in our galaxy could produce millions of neutrino interactions in that tank over 10 seconds. Instead of a few dozen or a few thousand events, you'd get a detailed, high statistics movie of the collapse and cooling. Third, the huge volume and extreme cleanliness also make it a prime lab to hunt for proton decay, a hypothetical process predicted by many grand unified theories. One proton decaying out of something like 10 to the 34th protons per year is the kind of rate you need a megaton-class detector to even have a chance to see. On the other side of the world, in the US, the Deep Underground Neutrino Experiment, DUNE, is built around a different idea. Not water, but liquid argon. And not just a short baseline, but about 1,300 kilometers, roughly 800 miles of Earth between source and detector. A high-intensity neutrino beam will leave Fermilab in Illinois, travel straight through Earth's crust, and hit huge liquid argon time projection chambers in South Dakota. Each of those detectors is like a three-dimensional slow-motion camera for charged particles. When a neutrino interacts, the charged products ionize the argon. Electric fields drift that charge towards readout planes, and the electronics capture the pattern with millimeter-scale resolution and precise timing. That level of detail means you don't just see a hit, you see the full topology of the event: tracks, showers, branching points. DUNE will use that to pin down the neutrino mass ordering, normal or inverted, by looking at how oscillations behave over that long baseline for different energies. It will probe CP violation by comparing neutrino and antineutrino oscillations in a very controlled way. It will also be a sensitive detector for supernova neutrinos, especially electron flavor ones, because liquid argon is very good at seeing them. On top of that, DUNE is built with room for surprises: sterile neutrinos, non-standard interactions, rare processes that don't fit the standard oscillation picture at all. Meanwhile, at the South Pole, the plan is to push IceCube into its next phase, IceCube Gen 2. The current IceCube instruments about a cubic kilometer of ice. Gen 2 aims to extend that, with more strings of optical modules spread over a larger area and depth, and with additional arrays of radio antennas listening for radio pulses from ultra-high energy neutrinos. Above about 10 to the 17th electron volts, the interactions of neutrinos and ice can produce coherent radio signals that travel long distances. By using radio, you can cover huge volumes for the very highest energy events. Those extreme energy neutrinos could come from the GZK process, where ultra-high energy cosmic rays slam into photons from the cosmic microwave background and produce pions that decay to neutrinos. Catching them tells you about cosmic rays at energies far beyond accelerators, and about interactions in conditions we can't make on Earth. At the same time, upgrades to the denser, low-energy parts of IceCube push sensitivity to atmospheric and oscillation physics, letting you measure mixing parameters and mass ordering with a completely different technique and systematic errors than DUNE or Hyper-K. Bigger volume at the top end, better resolution at the low end, same core idea. Take a ridiculous amount of ice, wire it up, and let neutrinos paint on it. Beyond the detectors themselves, there are also proposals to fix one of the biggest weaknesses of current neutrino beams, the messy, poorly known initial flux. In a normal accelerator-based beam, you smash protons into a target, get a spray of pions and kaons, and let them decay into neutrinos. You can model this, you can measure parts of it, but there are uncertainties. If you want to turn neutrino beams into precision tools, you want to know the initial flux and flavor content as well as possible. That's where ideas like neutrino factories and beta beams come in. A neutrino factory would store intense beams of muons in a ring with long straight sections. As the muons circulate and decay, they emit neutrinos with well-understood spectra and composition. You know the muon energy, you know the decay kinematics, so the initial beam is very precisely defined. Beta beams do something similar with radioactive ions that undergo beta decay while circulating in a ring. Both concepts are technically hard. You need powerful accelerators, cooling systems, storage rings, and huge detectors at the far end. But if you can build them, you can ask much sharper questions about oscillations and new physics, because any discrepancy at the detector can't be blamed on not knowing your source. So why does all of this count as a revolution and not just more of the same but bigger? Because every time neutrino experiments took a big step up in scale or precision, they didn't just confirm what we thought, they forced us to rewrite something. The first detections proved neutrinos were real. The solar and atmospheric experiments proved they have mass and mix. Reactor and long baseline experiments nailed the mixing angles and hinted at CP violation. Cosmology tied neutrino mass to the growth of structure in the universe. Now, the next wave is set to attack the remaining big questions: the mass ordering, the exact size of CP violation, whether there are sterile neutrinos, whether neutrinos break any other rules in subtle ways, whether proton decay exists, whether there are anomalies at very high energies that point to new interactions. Lower backgrounds, higher energies, longer baselines, larger target masses, and better control of the beam all open new windows where the standard model might crack. Neutrinos started in physics as a theoretical patch to save energy conservation. They turned out to have mass, even if it's tiny, which already breaks the original standard model. They oscillate, switching flavor as they travel. They stream out of the sun's core by tens of billions per square centimeter per second. They dump most of the energy in a core collapse supernova. They leak out of nuclear reactors and from radioactive rocks under your feet. And they've been flying through space since the first second after the Big Bang. They shape how stars live and die. They influence how galaxies grow because their mass affects structure formation. They may be tied to why there is more matter than antimatter. They're everywhere in number, trillions passing through your body every second. And at the same time, they're almost nowhere in terms of interactions because they hardly ever stop. That combination, everywhere but barely here, is exactly what makes them so important. And the key point is this: passes through everything is not a cute detail about neutrinos, it's the main feature. Because neutrinos barely notice matter, they walk out of places that are totally hidden by light. They leave the sun's core in seconds while photons are trapped for hundreds of thousands of years. So when you detect solar neutrinos, you're seeing the core's fusion rate almost in real time, 8 minutes after the reactions, not looking at old light that spent ages bouncing around inside the sun. Because neutrinos pass through Earth, you can stick detectors under kilometers of rock and still see supernova bursts, atmospheric neutrinos, reactor fluxes, and geoneutrinos. You can use how they're filtered by the planet to learn about Earth's interior. Because relic neutrinos decoupled in the first second of the universe and then streamed freely, they preserve information from epochs no photon can reach. Photons we see in the cosmic microwave background only decoupled about 380,000 years after the Big Bang. Neutrinos checked out a fraction of a second in, kept going, and are still drifting through you today. Their transparency is what makes them perfect messengers from times and places you literally cannot access any other way. Once you accept that, you have to update what you mean when you say solid. On human scales, matter feels solid because of electromagnetism. When your hand hits a wall, electrons in your skin and electrons in the wall repel each other. You never let your nuclei get close. The electromagnetic forces push back long before that. That's why concrete feels hard, why a table holds up your laptop, why you don't fall through the floor. But zoom down to the femtometer scale, to where nuclei and nucleons live, and most of an atom is empty space. The nucleus is tiny compared to the overall atomic size. A neutrino doesn't care about the electron cloud much because it doesn't feel electromagnetic forces. It's only looking for those tiny weak interaction cross-sections with protons and neutrons. From that perspective, even a dense metal like lead is mostly nothing, so solid becomes a scale-dependent word. For you, a meter of lead, about 3 feet, is effectively impenetrable. For a visible photon, a centimeter of water, about half an inch, is already enough to scatter or absorb it. For a solar neutrino, a light year of lead, about 9.5 trillion kilometers, roughly 6 trillion miles, is only maybe I'll finally bump into something once. Your intuition about solidity is not a universal truth. It's a local hack built on the forces you evolved to feel. Now connect that to the fact that you cannot turn neutrinos off. There is no practical shield that blocks solar neutrinos, supernova neutrinos, relic neutrinos, reactor antineutrinos, and geoneutrinos all at once. You can curl up under kilometers of rock. You can sit at the bottom of the ocean. You can fly in orbit. It doesn't matter. The flux changes with direction and energy, but it never becomes zero. There is no neutrino bunker. The good news is you don't need one. At natural fluxes and energies, neutrinos carry so little deposited energy that they pose no danger. They're passing through you right now, through your organs, your DNA, your bones, doing essentially nothing on average. If one interacts in your body, it's just another tiny nuclear event among countless others from normal radioactivity. Instead of being a threat, neutrinos are a data stream. They are constant, unstoppable status reports from the universe about what nuclear processes are running. The sun is continuously broadcasting its core conditions in neutrinos. Every working reactor is leaking a neutrino signature of its power and fuel mix. Earth's interior is telling you how much radiogenic heat it's producing. Distant supernovae and black hole jets are sending you single, ridiculously energetic neutrinos that point back to where they came from. The universe is already running a neutrino internet. You're just now getting detectors good enough to log in. So here's the mental reset that's worth keeping. When you walk outside at night, don't just think of yourself as standing on a solid ball of rock under a starry sky. Think of yourself as a loose cloud of nuclei and electrons, mostly empty space, held together by electromagnetic and nuclear forces, sitting on top of a bigger cloud of mostly empty atoms that make up Earth. Through all of that, continuously, you have a storm of neutrinos from the sun, from old supernovae, from active galaxies, from the Big Bang's first second, and from radioactive elements under your shoes. They pass through your skull, your brain, the air, the crust, the core, the sun, and distant galaxies, almost every one of them leaving no trace at all. Every once in a while, one of those particles hits a proton in a tank of water, or in Antarctic ice, or in liquid argon in a mine and makes a faint flash. From those flashes, you reconstruct supernova collapses, measure oscillations, weigh neutrinos, test cosmology, and probe the limits of the standard model. So what is a neutrino, really? It's not just a small neutral particle. It's the simplest package of properties nature seems to use when it wants to move energy and information through matter without getting stuck. Almost no charge, almost no mass, almost no interactions, but absolutely central to how stars work, how the early universe evolved, and maybe even to why there's any matter at all. It's the universe's way of moving information and energy almost without touching anything. And now that you know that, solid and empty should never mean quite the same thing to you again. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.